now we're starting. Okay. What I want to do is let's stick with polar for the remaining time today. We only have about 15 more minutes or so, and I think it's important to have a good understanding of this, and then I'm going to reserve the vector stuff until the next class session. So we won't start on vectors until the next session. So let's say we take this. Let's say I give you a radius that's 0.1 theta. You have to be thinking of these angles here in terms of real numbers, not degree measure, but you have to be thinking radian measure. If you see an algebraic type of an expression involving your independent variable, you can't think of it as degrees. So this must be radian measure. What would the graph look, the rectangular plot of this look like? Beginning algebra. Y is a function of x. Okay, yeah, a very shallow linear function, right? A very shallow linear function where the radius continues to grow with a slope of 1/10 as a function of theta, right? So when you get to 2 pi, when you get out to 2 pi for your angle reading, in other words, think of that as one whole rotation on your polar graph, your radius is only going to be 1/10 of that, right? 1/10 of 2 pi is 0.2 pi. When you're at pi, halfway around a rotation, you're going to be at 1/10 of pi. So the radius is growing how? How would you say it in just English to somebody? How's the radius growing? What's this behavior? Linear, right? The radius is growing linearly. The radius is growing linearly. What kind of polar graph would you expect to see? Joshua? A spiral. A radius continues to grow as your angle changes. Your radius is growing, right? Continues to grow as you go around and around and around. You can go around multiple times. Okay, so the plot you should expect to see is something that starts with a 0 radius off the pole, and it's going to grow. And when you get to 90 degrees, it's going to be about 1/10 of 3, which is about 3/10. When you get to 180 degrees, it's going to be double that, right? See, if you're here at 90 degrees, actually, I didn't do that right. It's not at 1/10 of pi. It's a 1/10 of this, 1/10 of 1.57. It's about 0.157. And when you get to 180 degrees, it's going to be 1/10 of pi, doubled what it was here. And when you get to 270, larger. When you get to 360, right? Okay. You with me? Well, actually, it looks like every pi, I'm sorry, I said that wrong earlier about the ratios, is every pi, the ratio is, it looks like it's double, doesn't it? Okay. So it's going to look like this. And the radius is, what my drawing is off here. What I'm doing, I have an undistorted viewing window on the calculator right now. And so what I want to do is kick this into the calculator so you can see this. This is called an Archimedean spiral. Archimedean spiral. And I hope I spelled Archimedean properly. A-R-C-H-I-M-E-D. not sure about the IAN, but that's pretty close. Archimedean spiral. If you have linear behavior on linearly changing radius, that's what you get. Let's kick this into the calculator real quickly, and I'm going to have to change my mode. I have to change my mode to be in radian measure. And so now I'm going to go from 0 to, let's let it go around several times, okay? Let's say 5 times. That'd be 10 pi, wouldn't it? To 10 pi. Now, what's our radius going to be when we're at 10 pi? What will the radius be when we're at 10 pi? It'll just be pi, right? Because the equation was 1/10 of the theta. Okay. And I'm going to put tick marks every, how about 1/10 of a radian? Every 1/10 of a radian. And I'm going to stick with a square viewing window, undistorted viewing window, with the numbers 4.7 and 3.1. Okay? Here comes the pretty picture. Oh, very exciting. 2 times around, 3 times around. Isn't that neat? Do you observe the equal spacing as you move out radially? Along any radial line you see equal spacing. That's because of the linear behavior of the changing radius. Isn't that neat? Okay. Let's say something was moving. Let's say something was moving. Here's something in dynamics. Let's say something is moving at a uniform speed. Following this. Uniform speed. What happens is the forces change as you're at different radiuses, as you're at different radiuses here. And you can learn that later on in applied courses. Very, very nice. Let's change the structure of this equation slightly. Let's do the following. Let's make the radius e to the 0.1 theta. How is this radius going to grow? How will that radius grow? How will that radius grow? What's the operative word here? Exponentially. Thank you. The radius is growing exponentially. So this is going to be an exponential spiral. The graph, the rectangular plot, and here's your polar down here on this previous one. The rectangular plot of this is a nice simple, this graph is e to the theta over 10. What we've done to this function, e to the theta, is we have grabbed it and made it 10 times as wide. We pulled it out like this. Pulled it out like a big old rubber band. And so instead of going up really quickly like e to the x or e to the theta will go up, we pulled that thing apart and it's going to rise very slowly but exponentially in its behavior. Got it? So the radiuses now are going to be growing ever more quickly, aren't they? See the graph curvature here? The further out you get here in multiple spirals, multiple rotations, the further out you get here, the quicker it's going to grow. And look at the change. If these were uniform, the change here is significantly different than the change that occurred back here. See that vertical, that rise? Compared to that, and you get further out and it's going to grow even more. So which spiral, after a number of rotations, which spiral is going to be further out from the pole? Which spiral will be further out from the pole? The exponential spiral or the Archimedean spiral if you go around, say, 10 rotations? Huh?
The exponential.
Eventually, the exponential will always overpower something like this. Always. Does that make sense? Taking you back to your algebra background? Yeah.
Did you say eventually because of how stretched out it is?
because the fact that it gets steeper and steeper and steeper, and eventually this thing's just going to climb like a rocket. And the radius, that means over a small change in angle, that radius is going to grow considerably. Compared to over here, over a finite change in angle, it's only going to grow always the same amount. So, real quickly, I can take this without destroying this Archimedean spiral. Why don't I turn that off by getting on the equal sign and hitting enter without destroying it, and come down here and put in our e raised to the 0.1 theta and watch it grow. It started at a radius of 1. Oh, but this isn't a very fair race, is it? Do you see? I want to be able to compare those two things, because this guy already started at a radius of 1, didn't it? Whereas the Archimedean one started at the pole. So how can we fix this to make the race between the two a little fairer? Yeah, couldn't we come back here and simply subtract 1 from this exponential to make it start at the pole? And let it graph. Boring. Oh, there it goes. Oh, but this one looks like it's really still overtaking the Archimedean one already, right? Well, that's still not very fair for competition, is it? You with me on what I'm talking about? Okay, so let's come back here and let's let this factor be smaller even. How about 0.0 insert a 1? 1/100th of theta on the exponent, right? So now I'm making that exponential polar rectangular plot much flatter even. And let's see how it grows. Oh, we're going to fall asleep. It's working. Oh man, look at that. Be boring. Oh, it's just a little black dot, huh? Boring, boring. Who wins the race? Archimedes does, right? Archimedean spiral wins the race. So let's just let this race happen a little bit longer. We said we'd originally let it go 10 pi, didn't we? Let's let it go, oh, how about 3 times that? How about 30 pi? 30 pi. Three times as much. Just be patient. Just watch the pretty picture. Now that Archimedean spiral by now would be way out here, wouldn't it? What I'm trying to wait for is I'm hoping I'm going to see, do you see how it's just kind of building around the edge there? I'm trying to wait there. Now, come on. I'm trying to get it to there where it's starting to separate itself from all those other little pixels.
We need more still.
I need more still? Oh, this is kind of fun. Okay, do you see how you can sort of tune? You can tune one function to compare it to the other. And so what we could do is, it's still going, but what we could do, folks, is we could adjust that to where one would eventually overtake the other, and we could draw both graphs on top of each other and actually see at what radius value they actually touched each other. Here's what I meant by that, and then I have to stop talking. If I took this one, which was an Archimedean one, and I took an exponential one and reduced it so that it sat down here, took it down 1 to get it to start at the pole like we just did, right? And build one that sits here. Do you see what I'm getting at, folks? Here's the exponential spiral as a rectangular plot, and here's your Archimedean spiral, eventually there's going to be some angle out here at which they will have the same radius. And then beyond that, the exponential spiral will be out at a further radius. Okay? So that's going to close off the discussion on polar. And you've got a little bit of homework to do, but we're not going to look at that until after. That's not going to be due until towards the end of the term. So study up for the midterm next week, and we'll see you then.